Start. Hello and welcome back to Calculus 2. We're talking about polar coordinates. This is extremely important because later on we are going to upgrade two-dimensional coordinates into three-dimensional coordinates. So your x and y is going to pick up z, and these two-dimensional polar coordinates are going to split and either pick up z for cylindrical or pick up another angle phi to create spherical coordinates, which will give you more options for integration and setting up integrals to find volume and other stuff in Calc 3 next course, right? So polar coordinates are still 2D. We have r theta, where clearly r is the radius and theta is angle. So polar coordinates are still graphed on xy plane because that's the 2D. And you're still working with points and functions, okay? However, they're useful for certain type of functions, certain type of point. Well, point's a point, but I mean, the difference between the xy rectangular world and the r theta polar world is the way you get to a point. There's no difference in a point itself. What's different is how to get to a point. So I'll give you the example. In xy world, which is your rectangular coordinates, to get to a point, you will count 1, 2, 3, maybe 4, and then you will go up 2 units and you will call this 4, 2. So you went 4 units in x direction, and then you went 2 units in y direction, and that's exactly what you denote as x comma y, which is 4 comma 2. So that's how you get there. For polar world, r theta, the way you get to a point is you draw the radius, let's say 3, and then you swing that for theta value. So let's say you did pi over 4. And then this point here is 3 pi over 4. So you see, it's a different type of a way to reach a point. So in xy, you count x, and then you go 90 degrees, count y, up or down, whether it's positive or negative. But for our polar coordinates, you will always draw on the x-axis, you will draw your radius, whether it's positive 3 to the right or negative 3 to the left. And then you will swing that counterclockwise, right, if it's a positive angle, counterclockwise for the angle that it's given to you. This is still on xy graph. We at least used r equals 3, which is the x value, and then you swing. So with that being said, let's see how you do with a few examples. So graph 4 and pi over what? 4 and pi over 3. So graph this one. Well, that should be sufficient time. X and Y. X and Y. So I'm going to draw radius 4, and pi over 3 is about 60 degrees right here. So when we swing, it ends up being this point here. It's 60 degrees, right? All right, let's see, graph -2 pi over 4, whatever. -2 pi over 4. Okay, so this is, again, all of these are quick, guys. We have -2, which now goes to the left, and you still have to go counterclockwise. Flow of positive angles is always counterclockwise, so you will go -45 degrees. Right there is the point.
Why is it negative? 45 degrees?
It's not -45, it's positive 45 degrees, because from here, which is pi, and then you add plus pi over 4, which is this distance plus pi over 4, you are getting here, which is 5 pi over 4. So you added positive pi over 4, which is what is needed in your point. So you start at -2 on x-axis because your radius is -2, and then you go positive pi over 4. If this was -2, negative pi over 4, you would go up, right? Because the negative angles go to the right, clockwise.
So if we first do 2 points with x and then d1,
You always have to draw a radius on x-axis first. If it's a positive, you go in the positive x direction. If it's negative, you go in negative. And then you look whether the angle is positive or negative to go up or down, depending on the sign, because positive angles counterclockwise, negative angles clockwise. Good. The next order of business for these polar coordinates is to figure out what is the connection between the xy world and the polar world. Clearly they are graphed on the same xy plane, so they have to be connected through equations that can convert one realm into another. Conversions. Now, this is essential because of integration. When you want to integrate something that looks really nasty, it might be better to integrate that in polar world. And we'll see that next class. Right now we're going to talk about conversions of points, and then we're going to define function in polar coordinate, and then conversion of functions, because that's what we ultimately need to do the integration. So, if you take a look at a random point, which you can get to by counting x and a y, or swinging r, you quickly see that this triangle is a right triangle which contains all four entities. You have x, you have y, you have r, and you have theta. So simply writing three trig functions, sine, cosine, tangent, and a Pythagorean theorem, you have conversion from one to the other and back. So usually they teach you to memorize this. What I like to do is I like to put all four on a pile and then use common sense to separate them. So let me just write cosine theta, for instance. Cosine theta is clearly adjacent over hypotenuse. So that's x over r, right? So from here I can write x is equal to r cosine theta. I can also write sine theta, which is y over r, from where y is r cosine theta. And what is my common sense telling me here? The common sense is telling me that if I have both r and theta given, I can compute x, I can compute y, using these equations. So this must be conversion from polar into rectangular, polar to rectangular, because if I have both r and theta given, I can find x or I can find y. Oh yes, thank you. This is sine. Come on. Rectangular coordinates x, y. So you are going from r theta domain into xy domain. Now if you write the other two formulas, Pythagorean theorem, which is x squared plus y squared is equal to r squared, from there you can see that r is the square root of x squared plus y squared. And if you write your tangent, theta, as y over x, right, opposite over adjacent, you see that you can write your theta as the inverse tangent of y over x. Now if you look at these formulas, they are clearly rectangular to polar, because you have both x and y given, and you can find r and you can find theta. So whatever way you want to memorize this, you're going to want to use this a lot, these conversions. So in whatever way you want to learn this, you can do it. The way I like to think about this is just write sine, cosine, tangent, and then Pythagorean theorem, and then sort them which one goes where. If I have both r and theta, that's the formula that goes from polar to rectangular. And if I have both x and y in the same equation, well, then that's rectangular to polar, because I have both rectangular values given and then go to polar. So now I want to use this. Convert, let's say, 0.512, which is x and a y, to r theta, to polar. Well, I use my purple conversions. R is the square root of 5 squared plus 12 squared, which works out to be 13. And theta is the inverse tangent of 12 divided by 5, which you can approximate. If you change your calculator to degrees, you can write that in degrees. So I'm going to go into mode and then go to the third line and change it to degrees. Please remember that for graphing you need radians, okay? So for graphing you need radians, and for calculations like this you might want, and for your physics, right, you want degrees. Second quit, inverse tangent, so second tangent to give you inverse tangent, 12 divided by 5, and it's about 71.6 degrees. So about 71.6 degrees.
61, 67.
What did I do? Oh, for some reason I typed 15 over 5 instead of 12 over 5. Okay, I see. So 12 over 67.4, yes. 67.4 degrees. Good. So what is your r theta in this case? It's 13, 67.4 degrees. You can, have this theta in radians, like pi over 4, or you can have them in degrees, 45 degrees, right? So it's either. Now, since, most of you are engineers, you mainly deal with degrees. You will rarely, use your radian skills. So that's the conversion. And you can also convert, let's say, 3 pi over 6 into rectangular Cartesian coordinates by simply saying x is equal to r cosine theta, which is 3 cosine of pi over 6, which is 3 times root 3 over 2. So that's 3 root 3 over 2, which you can actually crank as decimals if you care. And y is r sine theta, which is 3 sine pi over 6, which is 3 halves. So the answer for this one is 3 root 3 over 2 plus, comma 3 halves. And you can go and you can get your decimals if you want to. Now, one thing that I want to point out now, and we are just going to make it much more clear when we transform functions, is that these two coordinate systems are not competing at all. They are not in odds with each other or anything like that. They simply supplement each other. What's beautiful in one coordinate system is going to be ugly and disgusting in another. So that's the beauty of this thing. So if you see, we are starting with a nice point 5, 12. And we get 1367.4. Now, I would have had over here 5 and 11. This 13 would be worse. It's just, I know that, 5, 12, 13 is a Pythagorean triplet, so I know that it's going to work out to be 13. But if you pick any two numbers here that are easy to graph on xy plane, chances are that you are going to end up with some horrible decimal there, right? For both numbers. So what's beautiful in one is going to be ugly in the other one. And then if you look at the other one, right? So the only one that stays nice is 0, 0, right? And then 1, 0 would stay nice. 1, 0 is still 1, 0, right? Because it's on x-axis. The angle for that is 0. And r is 1. So anything on x-axis stays exactly the same in both coordinate systems. If you think about it, 5, 0 is 5 on x-axis, that's the radius is 5. So you stretch it, but you're not swinging it anywhere, so it stays on a 0 theta. So 5, 0, x and y is still 5, 0 on r theta. But it doesn't happen for others. Yes? Well, that's the next part. So now we have time to talk about functions. In polar coordinates, functions are going to be r in terms of theta. So functions. R is a function of theta. So theta is the input variable. You have your domain, which is how much of a circle you're going to swipe, and R is the output, right? So what is the example? What is the equation R equals to 3? What do we get for this? You go, what would this be? Let's do the conversion, right? We know that conversion says that R is equal to square root of x squared plus y squared. Because you kind of want to convert this into the realm you're familiar with, right? So you swap this R with that square root of x squared plus y squared, you get that equal to 3. You square both sides, and then you get what? Ta-da! Yes. It's a circle with radius 3. Whoa. Such a crazy equation in x and y. So simple in polar. Just R equals a number. Do you remember the simple equations in XY world? Like what's x equals to 3? What is that equation? It's a vertical line through 3, right? And what was the equation y equals to negative 2? Horizontal line through negative 2, right? So when you look at this, you say, oh, wow, x equals 3, it goes through x-axis 3. Realize that y is not in that equation at all. Y can be any value. It's not restricted by the equation at all, which is the reason why y takes all of the points from negative infinity to positive infinity, and it's a vertical line through 3. So we are able to express the entire equation through x equals 3. It's a line. You will do the same thing in Calc 3, where the plane, your ceiling in this room, which is 10 feet tall, will be z equals 10. It can go forever in x direction, it goes forever in y direction, and any combination of these directions, x and y, it goes forever, which is why we don't actually use any x and y to describe that. It's just how high that plane is. So now, go back to r equals to 3 and realize that in a circle, you are only making sure that r is 3 all the time, and you let this theta to go from negative infinity to positive infinity. It draws this circle, right? I know that it can trace the full circle just from 0 to 2 pi, right? But you can just leave it switched forever. It will always be tracing the same circle for all eternity, right? Because r equals 3 is enough for us to show what that circle is. You can make it bigger by saying r equals 4, or smaller, r equals a half. But the trick is that you don't need to say theta, because it's r is 3 for all thetas you can think of. Just like for those lines down there, that x is equal 3 for all y's. So we don't write any y's anywhere. Now, what would be equation theta equals pi over 4? That's also a function. What would that be? What do you think? Very good. It's a 45-degree line that stretches infinitely right? So it goes through the origin and stretches infinitely. Observe that r is not mentioned. So r is 0 at the origin. And then r is 0.1, and r is 0.001, and r is 100, and r is negative million, right? So all different r's that I could possibly, right? And every tip of the arrow traces a different point, right? All infinity of them fill the entire line. So it's just that, the full line like this. Again, on xy plane, but this is the case. That's pi over 4. Do you see that it's actually going to be a pain in the neck to actually get y equal mx plus b, like 3x minus 4? That's not going to look good at all because it doesn't go through the origin, right? All of the easy lines, pi over 3, or anything that you can come up with degrees, they all go through the origin. But your line y equals 3x plus 4 will go through 4. It doesn't go through origin. So this should have disgusting equation in polar coordinates. And we can quickly show how that looks like. I know that y can be written as r, what? Sine theta, thank you. And x can be written as cosine theta, and I have plus 4. Yeah, go ahead, solve that for r. You see? It can be done, but it's just annoying. You divide everywhere by r, so that kills these two r's, and only one r appears at the 4. So now I have sine theta minus 3 cosine theta is equal to 4 over r, and then I divide by 4, so I have 1 over r is equal to sine theta minus 3 cosine theta over 4, and then when I flip the fraction on the left, I have to flip the fraction on the right, which gives me r equals 4 over sine theta minus 3 cosine theta. Does that look nice? No. Because this looked nice in x and y. So this is what I was telling you. You guys, whatever is beautiful in one domain, it's most likely going to be really disgusting in the other. These guys don't compete against each other to solve the same problems. They complement each other. So whatever is round, based on circle or ellipse, right? That is going to be done in a polar domain. And whatever is kind of edgy, right? We have these lines and parabolas and so on. That's going to be good for your x and y domain. And they do different things. The last thing that I want to say is now you're going to take your calculators and graph something. So we are going to first change the graph. I hope your window is still negative 6 to 6. I hope you still have negative 6 to 6 on x. So change that first if you haven't done it. X min negative 6, x max positive 6, y min negative 4, y max positive 4, and don't touch anything else. All right, leave the x scale to be 1 and all the thetas and stuff, whatever it shows. So do that first. And then, you have to change the mode. Go to mode on the line 4, change into POL, polar. And then when you change that, go into window and make sure you have negative 6, positive 6, negative 4, positive 4. Don't touch any of that stuff. Just leave theta minimum 0, theta maximum should be 2 pi, yeah, 2 pi. So theta max should be 6.28, blah, blah, blah. If you don't have that there, just type in 2 pi, and it will change into 6.2831, so on. So first you go into mode, and make sure you change it from parametric, if you use that last, into POL, polar. Then you go into window, make sure that theta goes from 0 to 2 pi, and then x min, x max from -6 to 6, and then those guys. All right, now when you have all of that, go y equal, and type in 4 sine 4 theta. Theta is the x variable. It will print theta when you push x variable. And then see what happens. So 4 sine 4 theta, and then push graph.
Yeah, something exploded.
In the little last line, all from the X's? Yeah. Whoa, I didn't get that. What am I doing? Is that a flower? Who else got a flower?
No, you put 6 pi.
I like yours better, but what did you do? Hang on. Yeah.
Why is this thing a step? Put
Yeah. Go back to it.
pi over
0.130896.
still not
I don't know. Just
Oh, did you change it normal and then change it to radius?
4 sine 4 theta.
POL, yeah.
What's your 4 sine
You
got to see do the thing.
I get
So are we all having a nice flower? No. You're not in radians.
Let me see.
I got it. Yeah, but it's not nice resolution. Go pi divided by, let's say, 24. Pi divided by 24. For theta,
Infinity button.
24.
Try, look for it.
Ben, you should have done that.
Pi divided by 48.
Should have done that for continuing graphics.
I might switch. That's what I'm doing now.
So guys, the shapes that you get here will be these flowers, the propellers, the conduits, so circles, so anything that is nicely, curved like that. You're going to get those kind of shapes. You are definitely not going to use this for triangles and things that have edges and they're rough, right? You got that? Good. You show George what to do? Yeah. So I hope you will play with this at home and try. Now, my question is, we are already over time. Do you want me to try and transform the function a little bit, or you want to go home?
You still have time on Tuesday with the review, so we can save the test?
Well, Tuesday we have a serious section to cover. It takes time for that to be done. We'll do it now? Just a little bit. So that gave us this. All right, they gave us a flower. So now just convert. Y equals 4 sine. You know what? I'm going to do 2 theta because the 4 theta will take about 15 minutes. 2 theta is faster. So if I want to do this, I will first write it, no y, r. Whoa. Whoa, r. I will first write this as 8 sine theta cosine theta because I use the formula for double angle. right? Which is 2 sine cosine, and then 2 times 4 is 8. And now I will plug in all of the conversions that I know. So r is the square root of x squared plus y squared. On the other side I have 8. Sine theta is what?
1.
Do what?
1, I'm not sure.
Well, we don't have it, right? So you have to write sine of inverse tangent of y over x. And then you have a cosine of inverse tangent of y over x. You see that beauty? Is this going to be eventually a nice xy equation? Hell no. But let's see, 2 more steps. So what I have here is, remember the triangle? I draw the triangle, I have a theta. There's another way to do this, but let's just power through this. So this is your y, this is your x, and this is your x squared plus y squared. So it's a sine, inverse sine, y over x. So I need my sine, which is opposite over, so that's y over the square root. And then I have a cosine of inverse cosine of x over the square root of x squared plus y squared. Now all of these cosines and sines inverse cancel, and you get your thing over here, which is 8 times xy, and then root times root is just x squared plus y squared. Move that to the other side, it becomes x squared plus y squared to the 3/2 equals to 8xy, and then you realize that there is no way to fish out y equal everything else. And you shouldn't have that, because you have, it's not a function. So you see the equation. So this is your equivalent equation in xy, right? So that's in xy realm, the rectangular coordinates, and r equals 4 sine 2 theta. So nice. There are derivatives to be taken and integrals to be done with this thing in polar coordinates, where it's, right? Equivalent equation in rectangular coordinates is pretty much useless. Useless in every aspect. You can't even graph it, you can't do anything with it. So that takes care of this section. We will talk about derivatives next class. So we're starting with the derivatives. So next section 10.3 is the calculus in polar coordinates. We will take a look at derivatives, and we will take a look at integration to find area under the curve, which is area of one of the petals of the flower, or area of the circle, or area of the intersection of the two, and things like that. So we'll have to, you know what you need to brush up on? Yeah, you need to brush up on some stuff. Maybe you want to write it down. Brush up on power reducing formulas, brush up on those trig identities that you will need, right? And the most important part, brush up on how to solve trigonometric equations. That's important stuff. So trigonometric equations, because that's what you need to be able to set up your limits of integration. Have to solve the equation. Yes.
Power reducing and
Power reducing is sine squared theta equals to what? Cosine squared theta is equal to what? You need to know tangent is sine over cosine and all that good stuff. I just used sine 2 theta is 2 sine cosine. Pythagorean identity sine squared plus cosine squared, and then secant tangent. And then how to solve trig equations, like 2 sine x minus 1 is equal to 0. Solve that, right? So yeah.
What do you mean when you say know how to solve trigonometric equations?
I just said that. Know how to solve trigonometric equation, because not if, but when you see this, what is the solution to this equation?
Find theta.
Find theta.
Okay.
So you will have this as sine theta
Oh, so that's not so
equals to negative 1/2. And then that happens when?
That happens
I'm
when
saying
theta
that
equals.
like
Oh.
Right?
Wow,
You
that's
can do the graph much faster than anything else. So it happens at 5 pi over 6, right? 7 pi over 6 and 11 pi over 6, right? Good.
Oh, so that's like going back to.
To pre-calculus, I know. All right, bye, stream.
What?